Okay. It's time to start. So, what I plan to do today is to give you, to summarize a little briefly what we have done so far, to get the whole picture on the board once more, to make sure that we're all on the same page. And I want to spend a little bit of time speaking about this sum-point analysis without any details, but actually to give you some kind of feeling for things that could happen, that will happen in the Aztec Diamond, that could happen in other situations, and sort of guiding principles for this type of random phenomena, universal phenomena that can happen, and how to prove it from a subtle point of view. After that, I want to actually give you a proof that for the partition function of the Aztec Diamond, counting the number of tilings of the Aztec Diamond, and I will do that again using Duits theory. And I will give you one of the most beautiful formulas from Duits theory, which is called the Lauréat of identity. I'll prove this with the proof that I think is nicest, I like the proof best. However, I've also spent some time on proving on the original proof of the Lauréat of identity, which has a very anecdotal story behind it, which uses also Chaire measures. So I will speak a little bit also today about Chaire polynomials and Chaire measures, because the way we have introduced everything is by non-intersecting paths. There is another way of doing things with representation theory, starting from Chaire functions and symmetric function theory. And this actually gives a very nice alternative view. And I don't want to go into all the details, but at least I want to present the basics of that and to connect it to things that we have done so far. Okay, so that's a little bit the plan for today. But let me just give you a summary again of what we were looking at. We're looking at Aztec diamonds. So maybe this time without slides, let me try to draw one on the board. This is an Aztec diamond. Okay, so let's do it like this. This is an Aztec diamond, size 3. I don't know what you think about it. I'm proud of the result. Drawing these pictures is always horrible. And we're going to look at tilings of those, right? So maybe this is a tiling. Shall we do like this maybe? And then maybe make it a little less trivial like this. And now I have to finish it like that, and then let's finish it like this. Okay, so this is a tiling of the Aztec diamond. And of size 3, and we want to so maybe I'll close the door. Looks like a double bouquet. Quickly close the door. Okay, so this is the Aztec diamond, and then we decided to draw paths on this. Instead of looking at tilings, we look at paths. And paths were done by doing a checkerboard fashion on it. First a checkerboard fashion, and then you see that you actually have 4 different types of tiles. And then I drew paths, like this. Right? So this one goes here because it's domino like that, but here the black square is up, so we go down, then we go straight, up, down. Okay. Yes. Here we go straight, okay, so there was a little boring, and this was also straight. It's also a little boring perhaps, but this is a way of encoding the Aztec diamond just by taking these non-intersecting paths. Okay? And okay, I didn't really like these paths because you see that one path is significantly much longer than the other one. And this is somehow not really what we want, because in the non-intersecting path picture, we have sort of paths that go from one side to another side, and basically the number of steps of each path is the same. So one way to do this, and I will use this again when I compute partition functions, is to actually draw another Aztec diamond below it. And actually, you can actually do a trick. You can actually start doing a corridor. I hope I do this right. And only then do a Aztec diamond. So like this. I draw a corridor like this. Yes, like I can draw a corridor like this. And yes, so I'm doing it like this. Is this what I want to do? Because now there is only one way of tiling this. I probably should move this a little to the right. I think I have a slight problem here. Yeah, so it's okay. Yes, like that. There's actually one way. If I take a little corridor like this, there's only one way of tiling this corridor, and that's by straight coordinate things. And then I can do another thing. I can put an extra Aztec diamond like this. Well, let me see if I can do this properly now. So I will actually now take another Aztec diamond of this size. Yes, like this, and like this. Okay, so I have another Aztec diamond like this. So I have one that is of size 3 here. Here it's n. In this case, n equals 3. And here I have one of n minus 1. And then I have this corridor, right? And then I draw it here, maybe another tiling. Here I can, nothing is forced. I can have a tiling maybe like this. And if we continue to the checkerboard fashion again, we actually get the black squares precisely inverted. So that it's a reflected version. Which means that if I draw these paths, I will get a configuration like this. Yes? Okay, so that's a way of drawing, just putting an extra Aztec diamond underneath it and just put some border in that. This will force all the paths to go like straight lines here in the corridor, so it's completely determined. And it takes a little bit of thinking, but not too much, to see that if you want to tile the big region, you will actually, there's only one way of doing that. It's tiling the Aztec, the corridor which is frozen in this one, so it really decouples. Okay? And the benefit of this is that we can now look at paths that really go from one side and they end at the other side, and we look at it slanted, so we rotate the picture, and then we get paths that start here and they end a little lower. And then we don't really like it the end lower, so we push them up. So we do the transformation that pushes them up, so they end up at the same place. And what happens then is that you get a non-intersecting paths on a graph that is of this type. Right, so just to get the whole picture again, and okay. Maybe I'll do one more. Like this, and they're all directed, everything is directed, and so on, everything is directed to the right or to below. And then what we have is that these paths, basically, they start from points here, 0 to minus 1, 0 to minus 2, 0 to minus 3, and let's just take until 0 to minus n. And the end here at the same height, 2n minus 1 to 2n minus n. Yes, at the same height. And they will follow like, okay, they can maybe do like this. I think this picture actually corresponds to what was, or maybe not exactly, doesn't matter. This is maybe not exactly the same as example as I drew, but you can sort of think here's another path, and then there is another path, and so on, and so on, and there is another path. And this path encodes this larger region. And the larger, so it also means that, by the way, that the only thing that we really need to care about, if you really want, is basically something that is above the red line, because everything below the red line is that's living here. Okay, so there is a nice line, and you only have to think about that. But the nice thing about this was that we have a nice way of analytic theorem, algebra theorem, to write the random configuration of paths in terms of product of determinants, and this gives us a way of seeing it as a determinant point process. Okay, so now let me say one thing. One way to, so we started with the uniform Aztec Diamond, and for technical reasons that I was a little bit sloppy on in the end of the last lecture, but corrected by that. So there is actually a nice way of putting a parameter A on that, and you have to be a little careful in that. I wasn't so careful in the end. So it's actually nice to first, instead of the uniform measure, to look at the probability measure on a given tilings, which is proportional to A to the number of vertical dominoes. Okay, so you look at the model. So the probability is not sort of uniform of all tilings. So you count the number of vertical dominoes, and in your tiling, it could be 0, could be everything, and you take A to the power limit, right? Which means that every domino here is basically has a weight A. So these have weight A. This is just weight 1. Okay, right? And what does that do? It means that in this directed graph, I have a weight A here, A here, A here, A here, and A here, and also A's here, A here, and A here. And the rest is all 1. So this is 1, 1, 1, 1. This is A, 1. This is A, this is 1. This is A, 1, and so on. Okay? And this means that we have so we went from the Aztec Diamond to paths, and then we go to a point process. We draw now points on these paths, like this. So I just look at each sort of section, where is my path, and then I have two different options. I choose the lowest one. That's important. If you would have an up jump, you would take the highest one, I would take the lowest one. And then these green points, they form a probability measure. They have the probability of having a certain configuration of points, right? So points y, let's call them yj, m, okay? Where this is basically the my axis. Yeah. So it's the full collection, right? So that's going from j is 1 to n, and m is 0 to n, but we have the endpoints are fixed. Yes, and this probability, this is proportional to the product of m is 0 to n minus 1 of tm plus 1, the transition to go from the points yn to yn plus k, right? So this is the point yjm, right? So So this is and you take this, and then you take a matrix, you take a sub-matrix of this matrix, and we have a determinant of that. Okay, and I assumed here that y0 is right. Y0 is just minus 1, right? So assuming that y0 j is y to m of j is minus j. Okay, once you have that construction, you know that this is an meta theorem. You know, once you have product of determinants, you have the meta theorem that tells you that there is a correlation kernel. That correlation kernel involves inverting the ground matrix. The ground matrix is difficult, but if the ground matrix is actually an infinite Duits matrix, we saw that we could invert it, and we have a nice formula, right? So that's the case here, because in this case, Tm n plus 1 y prime is actually not a Tm, this transition to go from one to the other is just the Lauréat matrix associated to the symbol AM, and I put a twiddle in there. I mentioned last time that you have to pay a price at some point. And this twiddle notation, remember, a twiddle m plus 1 of z is a m plus 1 of 1 over z. Right, so that's the twiddle notation. And then a m plus 1 of z is either 1 plus a times z, or 1 over 1 minus a over z when m is even, and this is when m is odd, because these are these columns. So that was the setup. This is just a convention that I like Lauréat. You know, the twiddle just comes from the fact that I like to have the negative Fourier coefficients in the upper triangular part, not in the lower triangular part. Otherwise, I could have dropped the twiddle. So why don't you do that? Well, then you run into other convention problems later. So you have to pay a price. I paid here. Okay, and this 1 plus az, you should think about, these are the sort of first steps, these are the Bernoulli steps. This is really the z transform basically for the Bernoulli random variable, and this is the geometric variable with force like that. Right, so we take at each step, we take a Bernoulli or a geometric step up or down, and then we glue them together, and then we condition the paths to end here and there, and they also have to be non-intersecting. This gives you this determinant. And now the whole point was that if you set n to infinity, you can actually get a nice kernel for this. So when as n goes to infinity, right? So if the number of paths go to infinity, then you have a nice, then actually, you know, so basically the lower you drop and you don't care about, you only look at the top part. But then you have a very nice formula that goes as follows. So we have, okay, I call it xy, okay, yes. Okay, so maybe I should have, yeah, it's okay. I should maybe have used x instead of or, yes, no, let me do that. So we get a kernel, which is given in the following way. It's minus the characteristic function, depending on that x is less than x prime, of just tm1 to x1 to x2, of y to y prime, sorry, x to x prime, yes. And here the notation is that tx, let's call it x prime, this is the product, this is just t of x to x plus 1 times the t of x plus 1 to x plus 2, and so on to tx prime minus 1 to tx prime. Okay, that's the notation I have here. Okay? So this is just taking the product of the matrices, it's just a transition to go from y to y prime from time x to x prime. Plus, and now I have 1 over 2 pi I squared times what? Times the integral here, dz, integral over dw. I like this notation. And then here I have 1 plus a w dx prime times w minus a to the n minus x prime divided by 1 plus z to the x, z minus a to the n minus x prime, sorry, x, sorry. And then here I have w minus z. Oh, yes. times z to the y over w to the y prime. Yeah? And these contours here, what are these contours? These are just Fourier coefficients. So w is basically on the real line, on the circle. Z is also on the circle. But remember, in our computation, there's a pole when w equals z, and we got to this pole by doing a geometric series. When we did the geometric series, w needed to be bigger than z. So let's say that w is like rw, this is rz, and we should also make, I have an a here missing. We also have a pole at minus 1 over a, and we have a pole at a, and at 0, and at infinity. Okay, so let's do this again. So here is C. We have a pole at 0, pole at infinity. We have A here, and right, and we have minus 1 over A here. And our circles need to be around this, and they go in this direction. Okay, so this is maybe the integration over W, right? And this is the integration over Z. Yes, it has to be like this. Yes? Okay, so that's the situation. And now you see why I cannot really, if I would have taken A equals to 1 immediately, I get problems because minus 1 over A and A is at 1. It's at the surface, at the unit circle, and I get a little bit of an issue, convergence issue. And now it's useful to have A between 0 and 1. To first set this model. Now that I have this formula, everything is continuous in A, and analytic in A even, I can set A to 1.
So why do you want to take A between 0 and 1?
Why do I want to take A between 0 and 1?
Yeah.
I could take A also be bigger than 1. That's not a problem, but then I have a problem that I have to put this one inside and that one outside. Mm-hmm. It doesn't really matter. But actually, actually it does matter a little. Yes, because I mean, you have to think, right? I mean, if A is actually, yes, it does matter. I need A to be less than 1, because in the Wiener-Hopf factorization, I need to have everything that was analytic inside and outside. Right? So if you have analytic inside, this here has a pole at A. So this is analytic outside the circle. This is analytic inside the circle. So if you take A to be bigger than 1, you can do that, no problem. But then the Wiener-Hopf factorization switches the factors. Okay. So then you can do the computation. It's totally fine. I mean, of course, it should be the same, right? But it should lead to the same result in the end, setting A to 1 from above or from below. But the road to that is different because the Wiener-Hopf factorization is different. It will lead to the same result. So it's a good exercise if you want to see that you really understood this computation. Do the whole thing with A bigger than 1 and do the computation again.
And when A equals 1?
So when A equals 1, then I will do that now because it's the uniform case. Now I can say, look, I mean, 4 years I was working on the circle, but I mean, everything is analytic in an angular. So I can basically, I can move my contours as I want because of analyticity. So now I actually just set it to 1. Then my contours just don't really have to be like this, but this is a contour at gamma z, and this is the gamma w, and this is gamma w, and this is gamma z, and I just let them go around 1, 0, and but it cannot go around minus 1. So I just take any sort of deform my contour so that it goes around the poles that it should go, but not the other one, and so on. Okay? And w, this one should be around the gamma z. And now I can just set everything equal to 1. By continuity, right? So this is continuous in A, the whole model is continuous in A, and it depends analytically in A. So once I have the answer for the correlation functions, depends analytically on A, it should just set A to 1, it's no problem. And this is the formula that I worked with last time. Okay? So now let me remind you how that worked. Well, that was a saddle point analysis. So let me remove this now. So it's a very beautiful thing. So I'll write this now basically, and okay. So let me just forget about this part here, the single integral. That's never really the difficult one. The difficult one is the double integral. This is always something very explicit. Once you know how to deal with this, you always know how to deal with that. Okay? But the point is that this is of the following form. Right? This is of the following form. It's e to the n of w. Maybe it depends, right? At w over a to the n of fz. Okay? And then we have 1 over w minus w minus z. Okay, where f here, of z is what? Well, we get x over n times the log of z, 1 plus z. We get plus n minus x divided by n times the log of 1 minus z, minus, what do we get here? Yes. Minus a y over n I forgot this one, sorry. Of yes, this function. Okay? So it's basically that form. If I have w, then I have to put an x prime here. I have to replace x by x prime. But if I have z, I have just x and y. Okay? Sorry. I have a feeling actually that. Yeah, sorry. Sorry, I actually did another change of variable. I apologize. This here should also be an x here. Yeah, sorry. Sorry, let me write this again. So I didn't do any analysis here, so x plus y prime plus n. Yes, and this is no z. No, I do it. Sorry. Let me just write it slowly. Z to the x plus y plus n. W to the x plus y plus n. I'm very sorry about that. Yes.
Could you please explain again why the a disappears?
Oh, the a doesn't really disappear. So if you have a fixed a, there will be an a there. So if you want to study that model, which you can, you can do it with the same technique as I did. I just want to only now take the limit a to 1 to go to the uniform case. Okay, well, just do the analysis for the uniform case. But actually, it's an exercise to the reader. There's absolutely no problem in setting a to be less than 1. And you do the same analysis, just see what comes out. If you want to check that you understood everything, do the general analysis. What you will get is that it will not be a circle, but it will be an ellipse. So it's an Arctic ellipse. So there is actually, and it must be because if you favor horizontal than vertical, there should be more horizontal and vertical, which means that these frozen areas below and above, they are larger, and the ones on the left and right are smaller, and fits exactly with the elliptic form. Yes.
Also, when a equals 1, do you measure there be still normalizable?
Sorry?
Would the probability measures the.
Yes, you have. So I said it's proportional, right? So yes. So it's proportional to that.
So will the normalization constant be something finite?
Yes, because this, yes. And that's very good that I took vertical and not. Yeah, we can actually still normalize. I mean, there's a normalizing constant that is just coming from this partition function, and something in the middle. Right? In the middle, the weight is all 1, and that's what I set to infinity, so it doesn't really change.
But it's finite for all weight.
Yes.
Because it's deterministic in the middle, right?
Yes, in the middle it's deterministic, and actually, I mean, this is proportional, right? So you have to normalize it, and actually, even then, if you normalize it, it will still have yes. You just get 2 copies of the Aztec Diamond, basically. We'll actually do that when we compute the partition function. We will actually see that. So once again, so you don't really take a equal to 1. So I just take a equal to 1 now because I want to be a little. I just want to do the one case. I don't want to have parameter floating around. So again, this was n plus x plus y. Okay. And now the point is that I will set this parameter now. So you have to think, right? The Aztec Diamond will be large, right? So n will be very large. Okay, so x then also goes over from 0 to n. This will be my scaling parameter. This I will be called psi of n of log of 1 plus z plus 1 minus psi, right? So I will just roughly say that, right? Times the log of 1 minus z minus, and I will call this guy 1 plus eta. Okay? So I'll take those together.
So psi log 1 plus z.
Yes.
Instead of psi over n.
Yes. Right. So we go here on this direction was so this direction is psi and this direction is eta, and the Aztec Diamond now in these coordinates psi and eta is basically like this. Yes. So this is basically the Aztec Diamond. It should be from 0 to capital N, but I've scaled everything in the eta psi coordinates. It's really a square. Okay? And it's just a rotated version of this Aztec Diamond. Normally it's like a diamond, but now I rotated it, right? That's what I already did when I went to the paths. Remember that the paths I actually did a little, I did a trick to let them move up here, so that they end they start at the same point. Now actually I'm undoing that trick, and undoing that trick means that I send this to one parameter, and that's just this eta. I explained it last time a little bit, you have to be a little bit careful, but now I sort of undo that transformation. I really look, this is the Aztec Diamond, right? So the paths, they basically go from this here, the paths go from here to there. Okay? This is the Aztec Diamond. So this is one corner of the Aztec Diamond, this is another one, this looks like that. Okay, so let's
So
move
the
this.
the f is really 2 functions, right? One with the prime and one without.
Exactly. So now it depends. So you should hear, yes. So this has parameters, right? And this has also parameters, and these parameters are different. So I should actually say that this is maybe the f of psi eta, and you can get the same thing with the primes. Right? It doesn't really. They're there. Yes.
So is that log 1 minus z or log z minus 1?
Sorry, this is log z.
The other thing, log.
This is z minus 1. Right. It doesn't really matter, because z minus 1 and 1 minus z, of course they are different, but in fact difference is a multiple of 2 pi I, and since we're exponentiated and multiplying with integers, that doesn't really matter. Or maybe it's a pi I, but then it's a minus 1 something, it's a conjugation factor, gauge factor, so it actually doesn't really matter. So now the whole point is that you have to look at the subtle point analysis, as I said last time, right? Everything here, if n grows large, these integrals, they come from points where the f and the f is maximum or minimal, depending on if you have it in the denominator or the numerator. Okay? So you have to look at these critical points and then deform to saddle point analysis. Okay, so that's what I did last time. So let me just briefly recall. What we need to solve is the f prime of z equals 0. And it was very nice. F prime of z of 0 is actually a quadratic equation. Quadratic in z with parameters, right? Sine eta. Okay, so you just do that. It's a very simple thing. The logs disappear. You can just write down the equation. I actually wrote it down. I don't know. Let me just go quick. But it's a quadratic equation. There are two saddle points. And now we have there's a discriminant. Is the discriminant? Let's call it the discriminant of the equation. And okay, this discriminant can be positive or negative. And that was very important in this analysis. Okay, so now we can say we look at the calligraphic D. This is the point where all xi and eta are such that the discriminant of xi eta is negative. Then we have two complex conjugate solutions. If we do that, then it turns out that this is exactly a circle. So this turns out to be the circle sine minus a half plus eta plus a half squared is a quarter. Am I right now? Or is it, no, it's not a quarter. What is now the it's probably a half, right?
Quarter should be the radius squared.
The radius, yes, should be the radius squared, so it's a quarter. So why doesn't that match my feelings? Maybe I'm doing something wrong. Yes, it should be okay, but yes, of course, yes, it's okay. Okay. It's too early for me. Yes. So this will be this. You can just show that this is when the discriminant equals 0, and that means that we get here a circle, and this is exactly the Arctic circle that we thought. And then we have a sort of a table. If psi and eta are in this calligraphic D, right? So this region, this circle, then there are two complex conjugate solutions. So two complex conjugate saddles. And if psi eta is in the square, but outside, right? Minus e, then we have two real saddles. Okay. And then if psi eta is actually on the circle, on the radius, then this is a double saddle. One double saddle. Meaning that also the second derivative is 0. Right? So that really describes everything. So, for example, if I take, let me take the square again. Here's the square. If I take a point here, then you will find the following. Then you will have two saddle points that are here on the real line, on this part of the real line. Okay. This is just something you compute. I mean, it's a quadratic equation. Everything is very simple to compute. If you're just a little bit, if you cross this circle, you will have a saddle point analysis, you will have saddle points like this. Okay? It will be in a complex plane. So let me maybe draw a little bit like this so I can get everything in line. And then of course, if you're exactly on the circle, these two actually merged. So this is a double saddle. Okay? So it's sort of, you know, if you walk from this corner to the center, you will find two saddle points here. They merge like this on the circle, and then they split into two. And okay. And I showed you last time that you can prove, right? You can prove the following statement. Let me draw this now away. Take this away. That there's a very nice statement that says following. So that if psi and eta are not in this here, then we will see, or actually, yes. So if psi and eta are not there, then the kernel will converge to either 0 or 1 on the diagonal, right? So on the diagonal, so let me write it like this, right? So now we take 2 points that are the same. The density, right? So these are not primes. I don't have primes here, just look at the diagonal. It's the probability of having a point in our path process at this point. This will be either 1 or 0, right? And either 1 or 0, that means that there are either particles or not, and it's frozen. It's a 0, 1, you know, there is no randomness. There is either a point for probability 1 or there is no point. And this is for all these points here. So it's really like frozen here. Actually, here it will be 0. Here it will be 0, here it will be 1, and here it will be 1. Okay, you just compute it. And there's another theorem that if psi and eta is indeed, and we have omega psi and eta, that's the one, that's the saddle point in our upper half plane. Then what? Okay, then this diagonal of the kernel, so the probability of finding a point at the point psi eta will converge to the argument of omega psi eta over pi. Okay, so this is omega psi eta, and this is omega psi eta and bar. Okay, so this was a little overview actually of what I've taught so far in all the lectures. I think I also had a very nice statement, by the way, that I think you should remember, is that actually the map, there's another theorem, the map that goes from psi eta to this omega psi eta is a diffeomorphism. From D onto the upper half plane. That was a very nice statement also, which you get for free. And I mean, you get for free here because this is, you know, everything here is, I formulate everything abstractly, but remember, this is just a quadratic equation that you have to solve, and it depends on the parameters like C, X, I, eta. You just check it by hand. I see.
Why is that important?
Why is that important? That's not really important here. Okay? So it's not really important that it's diffeomorphism. It's a nice statement. It does show that, no, it's not really important at this point. Later, so maybe later in the course, I hope to give a proof of that. If we get to that, there is a nice statement about the global fluctuations. Okay, the global fluctuations are described by the Gaussian free field. I don't know if any of, does this say anything to you?
Yes.
Yes? So if, let's say something, so the Gaussian free field is defined on a domain. It's not this domain. It's the upper half plane. And you need to map first the disordered region to the upper half plane to push it forward, and you use exactly this map. So then it really becomes important. And yes, so it's a nice statement in itself, but it's actually important.
And why is that a theorem? Because isn't omega psi eta explicit in terms of psi?
Yes. So it's not really, yeah. So that's what I already said. Like it's not really a theorem. It's just you check it by hand. That's
right.
true. It's very easy in this case. But I write it as a theorem because if you would start looking at other types of models that look sort of similar, you'll have the same statement.
Okay.
So I just sort of I put things in a way that allows for generalizations. Okay. So this is a typical picture that you will see. Okay. And for example, if you know anything about the variational problems for tilings and dimers and the complex Berger equation and so on, this is actually a complex structure. It is in this case it's extremely explicit, so we don't have to think in those abstract terms. But if you want, this is sort of the typical behavior. This will always be the homomorphism. So it's not important for us yet, but it's a nice statement to remember.
Okay.
So what happens then finally, let me just say what happens when we are exactly at this point. What happens here if we have a double critical point here? I didn't really say that last time because I didn't have time. And definitely no energy. So let me say a little bit about this. So what happens if you have 2 points that sort of collide? Okay. Now, let me just remind you quickly. Last time I drew them, you have not only to find the critical points, you also have these contours, right? These contours, gamma z and gamma w, and you have to deform them through those saddle points. And which means you have to deform them using the steepest descent paths, right? So one path here, that was this one. This is the z1. You can show that it's the steepest descent path here, or ascent actually in this case, is going like that. This one goes like this. So this will be my gamma w. I will deform my gamma w, and I will deform my gamma z such that it does that. And now my board is too small, but you can see that this is not really a pole for z, but it is a pole for w. This was a pole for, -1 is a pole for z, but not for w. So it's okay. Right? And then these are the paths, and I deform my gamma w like that, and I just take the limit n to infinity, and you'll see the whole contribution just comes from these 2 points. And I just write it out what it is, and you'll see that it actually doesn't only converge to 1 and 0, it does it exponentially fast. So now if you're in this case, what happens? Okay, then we have the green, they will go like this, and the red actually goes to infinity. So, okay, right, so they pass through these points, and now I deform gamma w to this one, gamma z to this one, and then I have a problem because in my integrand it was 1 over z minus w. So when I do that, I pick up a residue. And if I compute the residue, I basically get this argument. It's a simple concept. That was very simple and very quick and very nice. Then you still have a doublet to go, and you have to do that analysis at that point. If you do the local analysis, you will see that it actually also converges to 0. Not exponentially fast, but with 1 over square root of n. Okay, so that's what I indicated last time. So today, we are in this case, and what happens now is that you basically, yes, of course, let's screw this up. Why? So what happens now, if you have a double saddle point, remember if you have a normal saddle point, it really means you have a saddle, 2 directions where you go up, 2 directions where you go down. Now we have also that the second derivative is 0, so we actually have 3 directions where it goes up and 3 directions goes down. This is sort of it's a little bit more singular. And if you see what happens, you draw what happens, you will go like this, and you will go like that. And this point here, if you zoom in, basically this angle is going to be pi I over 3, and here it's minus pi over 3, and also this angle is pi I over 3. Right? It needs, because it doesn't behave here, the f doesn't behave like a quadratic, it behaves like a cubic. Right? So if you do your saddle point analysis, so if you are at this critical point, and you do your critical analysis, then you will have to do a cubic term, right? So locally around that point, around the saddle point, so let me call this again omega, right? So this is correct. I have to introduce now not variables with a half, but with a quartic term, with a cubic term, which give me, if I multiply this by n, this will give me n of f omega plus, well, cubic u times f3 of omega divided by 6. Right? It will be more or less a cubic term. Yeah? So if you do your saddle point analysis, you see that the behavior is around the saddle point, it's cubic. Okay? So that's sort of the difference with just doing the analysis with what I did before with performing looking at Gaussian integrals. I don't get Gaussian integrals, I get integrals with cubic terms. Okay? Yes? So I will just write down the result, and then I will discuss a little bit the result. But the whole point is, I hope it's clear that if you do the saddle point analysis, which is not easy, so it's really a good exercise to do it. You should do it at least once in this course, I think, for yourself. To really do the saddle point analysis at the cubic acid.
So could you please explain how the pi over 3 comes?
Because basically the function f here behaves like a cubic. It's because it's a double saddle point. We have two saddle points that collapse, so around it it's no longer quadratic, it's a cubic term. Right? The local variable, the first term, if you do a Taylor expansion, the first 2 terms vanish. Not only the first derivative, but also the second derivative. So it's a cubic. So if you now check, if in a cubic you check where the real part is constant, you have 6 rays. Right? So we will actually also have, if you really want to be complete, you actually, if you really want to be complete, there will also be, this is also, the real line is also part, also there, the real part. So in the red line, the real part is, I guess, increasing. Yes, in the red part, if you relieve from this point, the real part will be increasing a lot, along these lines. And along the green part, it will go down as much. Right? So these are perfect because then you have in the integral, these are the contours you want to deform to. Then everything comes just on a local analysis here. And the local analysis will just give you a cubic term. Okay? So let me now write down the formula. But before I do that, I don't want to just write down the density. I want to actually look at the local scaling limits. Okay? So what I want to do is the following. So this is another. So what I will look. Okay, I don't have much space on the board. Yeah, so I can erase this now. So let me just zoom in here. Okay, so I'm gonna take. This is our Arctic Circle. Okay, and I'm going to look at this point here. Okay, so this is really the point that goes like from this part. Let's just really look at this part. So now I'm going to zoom in. I'm going to zoom in around this point. I want to know what is the local process. If you zoom in, you will find that there is some path here. I don't know if you remember these pictures. Maybe I should show them actually. are some paths that go like this. I don't know if you remember from the pictures. Maybe I should have actually illustrated this on the computer. I'll do that in maybe before the break. I'll set up the computer, otherwise it takes time. There are some paths here. Okay? And now it turns out to cover these paths, what we want to know is to cover these paths, we need to sort of look at the right window. If we would scale like we do in the bulk I didn't scale at all, I just looked at the dominoes. Right? Remember this from last time? By the way, I put up some lecture notes from last time also. I forgot to do that last week, so I did it now. If you look, you can see it's sort of discrete scale. Here, the right scaling is actually depending on this direction. If I look at this way, I have basically two directions I can look in. I can look in this direction, and I can look in this direction. So that's the direction 1, 1, and the direction 1, minus 1. Yes? And in this direction, it turns out the shapes of the structures, the random structures you see, this path, there are fluctuations in this direction and that direction, and they have different scales. So I need here to have here, so this is the xi eta, right? So this was xi eta plane, so I should probably take n to the minus 2/3 in this direction. Okay, so this scale here, the fluctuations are of order minus 2/3, but in this direction they are of order n to the minus 1/3. Okay, so if I would rotate and zoom it, I really get a path like this. The fluctuations in this direction n to the 1/3 and minus 2/3. In this direction it will be n to the minus 1/3. Okay, that's where the scales are.
Did you see it by inspection or?
So how do I see it? I see it from a technical reason. Because if I plug if I plug in this scaling, I'll get the right answer. Okay? Now that's a very bad answer, maybe, not very conceptual. But from a technical point of view, this will make it work. So if you now look at k of n, and you look at this saddle point, right? So let's look at the critical point. So this is really the double saddle point. And now when you add like some constant times n to the minus 1/3. Right. So I have to, what am I doing? I have to look at this point. So it's n times xi eta, critical. Yeah. So this is really this critical point here. This point here is xi critical, eta critical, okay? So that's on the circle, or C from circle. Plus 1 times n to the, well, I had n to the 2/3, but I multiplied it by capital N times constant C1 of S1 plus 1 minus 1 times n to the 2/3 times C2 times T1. And I do the same here with the second variable. Okay, so let me call this S and T. Okay, so now I look at two different points, S prime and T prime. So now these coordinates now are S and T. These are my local coordinates. So I get an S prime and T prime. This will converge, okay, to a kernel. I wrote down the answer here, so you just believe me. This is minus 2 pi of chi of what is it? Okay, I think that's actually okay, that's actually probably a little. Okay, that's actually wrong. So there is actually a first part, but I didn't update the coordinates properly, so there is a mistake in the notes. So there is a first part. I'll just do it like that. I have to think a little bit. Maybe it's correct, but I have to double check if it's correct because I forgot that I rotated my coordinates, so it's in the wrong order. But the most important thing that this I did correct, is this part. Now I get integrals, double integral formula, e to the u cubed over 3 plus s2 times u, s prime times u squared plus t prime times u over 2 divided by e to the v cubed over 3 plus s times v squared of 2 plus t times v du dv over u minus v. And right, I have to take n to the 1/3 times the C0. Yes. So there's a theorem that says, the theorem is there exists C1, C0, there exist constants. These are some numeric constants that are not very important. These are some constants, these are really not important. Such that if you take this limit of the kernel, it will converge to this limit. Okay? And what are these contours here? These contours, this is a gamma u, this is a gamma v. These contours are exactly like this, where this is gamma u and this is gamma v. And these are the local versions of these. Is that okay? Yeah?
In the, you said that in the s direction, the fluctuations of order n to the minus 2/3.
Yes.
So you multiply it with n to the power
1/3 here, because this is an xi-eta. This is the xi-eta coordinates, but now I have to write it in the xy coordinates, so I have to multiply it with n. So the minus 2/3 becomes n to the 1/3. Yeah, the scales are always a little. You have to. Yes. Okay. So, by the way, you know these 1/3, 2/3 scalings, they're not. You know, here, if you just plug this in, you do your saddle point analysis. You sit down and you just, you know, it's a rainy day. If it's on Sunday still raining, then you know you want to do something to do, then that's the thing you can do. You know, in Sweden we have lots of strong winters, so there's lots of time for such computations. So you just do it, and then this cubic term that you got from the local analysis is exactly this cubic term. Okay, and it's just an exercise. It's a tedious exercise, but it's just an exercise. This is very nice because remember I discussed when I discussed the saddle point analysis I did as in a special case the Airy function. These are exactly Airy functions. These are integral representations for Airy functions. Right? So remember the integral representation for Airy functions.
So these contours, they go around this critical point? Or
So these contours here, we have taken n to infinity.
yes.
So we deform the contours like that, and then it turns out that the only thing we need is everything that is around there. The rest we can throw away. And then we set n to infinity, and that just means that these are just some contours that go to infinity at an angle 2 pi I over 3, and here it's pi I over 3. Sorry, pi over 3, 2 pi over 3, just the angles, no I don't need I. Right, so the angles just go in that direction, or e to the pi I over 3, e to times infinity, right? So they go in that direction. They really just come from the local analysis here.
Right, and then I can just move them around. Right?
And then you can move them around how you want. You have to be a little bit careful because you don't want to, you know, if they cross, you pick up a residue. Right. So what I do actually, I don't really let them cross exactly, but when I zoom in here, I just make them a little bit right and left somehow, like a small little deformation.
But when they are on in the first picture, they go through the same point, or?
So in this picture,
Yeah.
they go through the same point, but I could also just make a tiny little epsilon difference at order n to the minus 1/3. And then I get exactly this picture so that it goes. But you can let them cross, it's no problem, as long as it's go tangentially, and then you will pick up a residue. It's okay. And the residual will be exactly this term. So actually, I think what I wrote in the notes actually is correct now that I think about it. So I have to just double check it.
And so we do have a power 3 in the 2 by I. 1 over 2 by I to the 3, the power is correct. In front of the integral.
No, this is just a square.
That's cool.
Okay, very good. So now let me just sort of like so basically this finishes everything. Okay, not really actually. So let us think a little bit again. Did I cover everything? Well, if you look at the saddle point analysis, right? I mean, what I do? Okay, either they are complex kind of, or they are real and different, and then they merge, right? So when they merge, okay. So basically, I have covered everything. Well, not really. There is a case that I didn't cover. It could maybe happen that those saddle points they come from the upper half plane, and they merge on the pole. This is possible. Okay. What is that? That's these points. These are exactly these points. And if you do the analysis here, you will not see area. Because you can't. Because, I mean, first of all, you can't because the fluctuations here can go, up and out. And here, you cannot go out of the Aztec Diamond. That's impossible. So it should not be possible. Right? And it turns out that actually, if you do the saddle point analysis, you can still do it. But you have to do a new limit. And what you find here is not this kernel, but you find the kernel for the Gaussian unitary ensemble. You find random matrices here. And I will not do the computation because it's annoying. I just, I didn't do it in the notes. In the end, I will do it, but it's actually a nice computation. What happens, it can happen at the poles, that the saddle points merge on the poles, and then actually one pole eats a saddle point, and you just have a single saddle point, and you will get an integral like that with a quadratic, because it's just a simple saddle point, but you keep also a pole here, and that's exactly the GUE term. Okay, so now you can play a game. You can think about you can think a little bit more. Let's think a little bit ahead. This picture is very general. I did it for the Aztec Diamond, but you can do it for much more general models. What could happen? Well, it could maybe happen that some saddle points, maybe there's a situation that there was actually, two saddle points merge, but they merge, but there was actually another saddle point also already. So while these two merge, there is a third saddle point that also merges to that point. So we have not a critical 2, but critical 3. We could sort of imagine that we're in a situation that here is an extra saddle point, and when these two come close, they actually merge with the 3 of them. That's possible. And what you will get then is not a cubic term, you get a quartic term. And this happens when the limit shape, sort of the Arctic Circle, in some models, I could show you pictures, has like cusp singularities. So this can happen, and then you just get the analysis is actually the same. From a 3 you go to a 4, and then you get musical representations for Pearson equations, Pearson, area to Pearson. Okay, so we can play, maybe continue our game. We can maybe have 5 saddle points merging. No, you can't. Which is a bit of a surprise. It's not clear from here. But somehow there is sort of a structural result that shows that you will never be able to get more than a third order Fibonacci. And why that is, there is sort of, that's a little, I mean, at least I've not seen it. At some point I remember, well, there was a recording, I mean, there was a paper appearing where they actually said, oh, it happens. But then they retracted the paper because it doesn't happen. It just doesn't happen. And there's actually a theorem that actually has also to do with this diffeomorphism that I spoke about. Actually, this diffeomorphism comes from there's a nice structure around that. From the diffeomorphism, you can also see what is the behavior at the boundary points somehow. And there is a classification of the types of behavior that can appear. Third order vanishing is the most that can appear. You can have that, you could have like poles of a higher order. There is actually a nice case where you actually have a pole of infinite order, so essential singularity, and settle points merging on the essential singularity, and then you get a tecton. So there are these things. But from a structural point of view, once you have a double integral formula, you run down your function, you compute the saddle points, and you just see how they behave, and that already tells you what the critical limits could be. Okay? There is as I said, maybe as a final remark, there is reasons for the n to the 1/3 and 2/3. These are called KPC scaling exponents. I might say a few words about that in a later lecture, why you get those. So for us, it's just a technical reason. I give a technical reason why this happens.
For all these different kernels, the scaling is always under the 1/3. The array here and
For the array, you will always get an n to the 1/3.
also the GUE pair.
No, for the GUE, you get a square root of it. Yes. Because in the GUE, I mean, the 1/3 comes from the fact that we have a double saddle point. When you go to the GUE kernel, we have two saddle points that merge, but one gets eaten by a pole. So you have only one saddle point, which means you get a quadratic term, it means you get a square root of n again, and the scaling exponents come from that. So the order of the critical point determines the scaling exponents and also the scaling limit. Yes.
What about the order for the other more complex kernels?
So then you will get a fourth here, because you get a fourth. You have to have a scaling of 1/4, and this will also be 1/4, and then one has a square root, and then maybe there is a 3/4 also. If you really want, you can put some extra, but you have to be a little bit careful how you set it up. But yeah. So, but structurally, this is just what happens. And it's really like, I mean, if you put these points in your saddle point function, you just see how it behaves around the saddle point. You'll just get the cubic terms, and since you're not exactly at the critical point, but a little bit off, you actually do get the quadratic in the first term because we're not exactly at the saddle point. It's like a little perturbation gives you an extra term. It's really trivial, but it's tedious to do. These are these things you don't want to do on the board, you have to do it at home. But I hope I have told you now enough so you can do it yourself. Yes.
Can you thought you obtain when you are into the fourth?
Yes.
When you are into the 1/4, what limit do you obtain?
What limit? So it's exactly the same thing. You get a 4 here.
Yeah.
And this has to do with not with, because
here you have 3C Wigan with the limit.
Yeah.
And in the cusp.
Yeah, so you get a different version.
Yeah.
Not the and it will so if you look at the Tracy-Williams distribution, it's a gap probability with the array function.
Yeah.
Right? So now we get the Pearce equation, which is the array equation is this equation, array prime double prime is x times array, right? Right? So the Pearce equation is the triple prime is x times Pearce. And you build a kernel in the same way from like you do from array functions, you do it now with Pearce functions, and you get not a Tracy-Williams distribution, but a different distribution. I don't believe it has a name. Yeah. But it's also a universal kernel. It's a little bit less. I mean, it's a little bit less universal in the sense that the array will always come when you go from like disorder to frozen regions. You will always get array, and if you get cusps, whatever, if these are just the usual cusps, the cusp will always give you something like gap probabilities in terms of this Pearce kernel. So the Pearce function. Does it answer the question? Yeah. So I don't know what time it is. Maybe this is actually a great time to have a break. It's maybe a little earlier. Or are there any questions about this? So in any case, so maybe let me make just a final remark. I hope you understand now that doing the scaling limits of the Aztec Diamond, now we're basically done, right? Because we basically understand all the cases and you can prove whatever you want. So the pictures that I showed from the first lecture, we are able now to analyze. Okay? Of course you can do more things. You can analyze the limiting objects. But I you know, you can wonder about what about these limiting objects that we get? What about the traceability distribution? What are the properties and so on? These are very interesting questions. I will not do that. But this machinery that I developed so far will allow you to do a lot of different models. And I don't want to continue so much more in this. I actually want to go to a little bit more advanced topics after today. I want to do in the last lectures I mean, this is all rather classical. So this was basically known for 20 years now. Yeah, I mean, okay, 15 years ago, this story was like quite close, I think. I mean, in different settings. So but there are some next level questions, and I hope I can spend some time on that. But after we take a little coffee, I want to actually speak a little bit about the Chaire process and about Nobody-Nakunkov identity, which I think is a very beautiful thing, which will allow us also to compute the partition function. I didn't really tell you what is the partition function. I told you actually on the first, I think the first slide in the first lecture, I told you there is a number for it. But this I will tell you how to do this again, interpret theory in a different way. So
what are the limitations of this approach? Can you consider more general domains or more general, or what are the types of diamond models you can consider? Other conditions and so on.
So this technique here, what I did now is this works exactly the same for all Chaire processes. So if you know what a Chaire process is, I will say a few words about it. But Chaire process. So remember that I looked at this not a second pass, and I let the number of paths go to infinity. I can take different columns. So for all the columns you can do, as long as you have Toeplitz transitions, you can analyze them. This includes hexagon tilings of the infinite hexagon. This includes the Aztec Diamond. However, it is always a little. I mean, the Chaire class is large. It has infinitely many parameters, and you can make beautiful pictures. You can really play with the parameters. That which just means that you are going to make this function f here, which was. I mean, we have basically a quadratic, right? F prime is quadratic, basically, right? So this can become much more complicated, but in principle, the picture is the same. So in a sense, it's also maybe not so interesting to do that. Now, so that's really what you can do with exactly this method. Now, there is other ways of arriving, like other models that you can do that also give rise to double integral formulas. Okay, so this kind of principles, there are variations to the principles that I did. For example, when you have interlacing particle systems, you can also set up these kind of machinery. You can also get double integral formulas. They're a little bit of a different type. You can also allow them to study those. So you can, for example, if you want, you can take a hexagon with maybe some pieces out, like a crazy domain like that. You can actually analyze with similar techniques. It doesn't fit in the framework that I talked about, but it's sort of related. So there is a lot of problems that are covered by this. This type of techniques, variations to it, also, but it doesn't do a general, not a general dynamo model. No, you always need to be able to formulate it. I mean, the whole point is that you always need to be able to invert this ground matrix by means of double integrals somehow. And once you can do that, these techniques apply, and all principles apply in the same framework. So it's not a general dynamo model, definitely not, but it's a huge class of models. relate to very interesting other types of questions. So I will actually do this after the break. For example, the Schur measure, the Plancherel, the Poissonite's Plancherel measure, you can sort of analyze the longest increasing subsequence. That's a famous problem that was solved 25 years ago. Basically, you can solve it with similar techniques here. So there is a lot of combinatorial problems that you can do, but you cannot do the general dynamo models, of course. Yeah.
But there's no technique that can do that at the moment.
Sorry, what?
No technique can treat the general dynamo model.
No, I mean, well, it depends. So there are, for example, some very interesting results by Hamel Agrawal, who actually shows, so he looked, for example, at collaborators. Sorry, they look at lozenge tilings of the hexagon. Lozenge tilings of domains, very arbitrary, and they have ideas of saying, like, look, if I know that I'm in a point somewhere that the region is disordered, then if I know I'm disordered, then I can actually prove the universality for these limits that you got that I computed, right? These local limits, that they are there. But it's very different type of techniques. That's a very different. So that's actually universality. So there are some universality results. Yes. Okay. And this can also be done if you're at the edge. So if you know that you're at the disorder, you know, if you have a statement that you know that you are at an Arctic circle or something, a boundary, then you know that there is a boundary, then it should be the area process. So there are statements like that, yes. Right. And this is very related to the results in random matrix theory. If you look at the GUE, actually in the notes that I posted, you actually, I also do the GUE and do the scaling limits of GUE with this type of methods, right? So you get the sine kernel limit, but you should also get the sine kernel limit for more complicated random matrix models. So if you just drop the Gaussian but just keep the independence, but you take some other distribution, you should still get that. And one way for how people did that is that you actually define some kind of dynamics on matrices, some flow, and that shows that very quickly, if you start with something, very quickly when you start your flow, you will actually stabilize to the usual GUE fluctuations. And this can go very fast, and then you have to show that this goes very fast, so you get a statement for a large class of random matrices. And for the tilings, it's a little bit similar. For tilings, you can put dynamics on there. I hope I actually have time to explain that. And so that's a little bit what in similar style, you put some dynamics. And then you show that very quickly when you run the dynamics, when you're in the disordered region, so if it's invariant under these dynamics, and then you should get this kind of limit coming out. Very rough in a nutshell. So these are very different types of ideas. Right, yeah. Okay, maybe it's time for a coffee. Okay. So welcome back. So what I plan to do for the rest of today is at least compute the partition function for the Aztec Diamond. And I will do that, there's various ways of doing this, by the way, but I will do it in a way that I like myself, because it gives me also the possibility to speak about a beautiful theorem, the Duits theory, that is very famous and an interesting background, and it's called the strong Sager limit theorem. Okay, so again, the setup is that we have a function f, take a function f which is defined on the circle, so it has Fourier coefficients like this, and let's assume that f is smooth. How smooth? Well, I don't care so much about it, but let's say that it's at least differentiable. Okay? It's not differentiable. It doesn't. So if it's not smooth, like if it has jump discontinuities or something, it's not continuous. It's not true. So we really need something that is sufficiently regular, but C1 is enough for now. Okay? You'll see quickly what I mean. Okay? Now I want to look at the determinant of the Duits matrix with this symbol. So this is the n times n matrix where we have e to the f 0, e to the f 0, and here we have e to the f minus 1, and so on, right? And here we have e to the f 1, and so on, right? So it's the Duits matrix, and it's an n times n matrix. So we take and clearly this is important because, for example, the LGV theorem has said that if you have transitions, right, from the path from one side to the other, and you have then the weighted sum of all the paths from one side to the other is actually the Duits determinant. So this actually tells you already this is actually Duits determinant is actually the in these cases. Of course, the symbol has to be special, and at the moment I don't care about special symbols, so we will do in a minute. But for now, it's just let us look at this general setup. Now there's a very nice theorem. There is the strong Seguelin theorem, and there's the weak Seguelin theorem. And the stronger is really stronger than the weak, so I'll just only talk about the strong Seguelin theorem. And it says that this determinant is e to the n times f naught plus sum of k is 1 to the 50 of k times fk times f minus k times 1 plus small o of y times n goes to infinity. Okay. So this is the strong Seguelin theorem. And this has a very long history. So we have we have the first term, the exponential of first term. The first term is called the weak Seguelin theorem. So including the second is the strong Seguelin theorem. And this is a very beautiful theorem with an interesting history. I don't want to go too much about this. And we will use this if I have time to speak about Gaussian free field. Actually, we will see that this theorem can actually also be explained can be used to explain the appearance of log-related fields in random matrix theory, but that's for a later time. So, but the theorem might come back later. But today we will only use it to compute partition functions. Okay, so I want to prove this theorem, and I want to prove it today if I have time. I want to prove it in two ways. One way using just Duits theory, not thinking about anything about what we spoke about, no probability. And then I want to revisit it using Schur measures, Schur processes, and actually show that actually there is a real probabilistic meaning to this. Okay. So first of all, it's a very beautiful statement that the fact that you have such an expansion for determinants it really depends on the structure of the matrix, right? So it's really a fantastic statement, and I will show you in the proof that it relies on some beautiful identities. So you will appreciate it even more when I give the proof. And actually, I will not prove. I will not so much prove this theorem. Actually, I'll prove something stronger. I will actually prove. This is a theorem. This is called the Borodin-Okhunov identity. And it is a very interesting story, by the way. And it says the following: the determinant of the Tn of e to the f, this is equal to e to the n times f naught plus the sum of k is 1 to infinity of k times fk, a minus fk, times the determinant of the identity minus qn of h e to the, now I have to be, now I have to peek. So let me write this as the determinant of identity minus qn of h to the e to the f minus f plus times h of e to the f plus minus f minus with a 12 times qn. And this is a finite exact expression. Okay, so f plus and f minus here, right? So I write f plus is the sum of k bigger than 0 of fk z to the k. F minus z is the sum of k less than 0 of fk z to the k. So f is f plus plus f minus, and e to the f then is e to the f plus times e to the f minus. Yeah? Just to get right, so these are just this f plus and f minus. They're just the splitting of this function in this form. Okay? And this holds for all n. It's a finite expression, it's not a limit. And these are the Hankel matrices. Right? Remember these were the Hankel matrices? Qn is also clear what that means. You remember what this is? Maybe not. So let me say, so if I have a matrix, Qn mean like multiplied with Pn on both sides, that's this one. So if I have a matrix, A is this, and this is the Pn A of Pn, and this is the Qn A of Qn. So it's sort of instead of the n times n upper block, it's the tail of the matrix. Okay? So this here says you take the product of two Hankel matrices, right? So I have two Hankel matrices, take product, this gives us a new matrix, it's complicated, and then we take just only this part. And then we take the determinant of 1 minus this part. Yes? Yes, is that okay? Or?
What exactly is this block decomposition?
Sorry.
What exactly is this block
so I'm just explaining what Qn does, basically.
Yes, but...
So if I have a matrix A, then this upper n times n corner, that's the Pn of A Pn. So Pn sort of projects on that, and Qn is just the rest. So Qn is basically identity minus Pn.
Yeah, sure. So these are these Hankel matrices now. Okay, maybe you should remind me what those are. But these are sort of infinite or half infinite matrices.
Yes, exactly. So again, if a Duits matrix, right? This is the matrix. The Duits matrix is A, J minus K, where J and K run from 1 to infinity. The Hankel matrix is this matrix. Right, so these are, I have A0, A minus, A1, and so on like that. So the Duits matrix are diagonal in this direction, and the Hankel matrix are diagonal in the other direction. Yes? Is it now clear? Yes. So now you see that this is a finite end statement. But I claim that the strong single limit theorem is actually just a special case, because what happens with this operator? This Hankel matrix has these diagonals like that, right? I told you F should be smooth. That means that the Fourier coefficients are dying out. So these Hankel matrices, these anti-diagonals will decay very quickly. So this is basically, you should think of this as like a compact operator, or maybe like a, maybe even just say finite rank, you will have finitely many Fourier coefficients. Then it's finite rank, right? So these are harmless. Now I multiply two of those, but in the end I take this part here. And this will only have coefficients that are dying out very fast. So when n goes to infinity, you can actually show that this goes out very fast. So this determinant converges to 1. It's just a determinant of the identity, which is 1. Okay? You can make this precise. I will do this in the notes, actually. It's actually a nice exercise to do this. You can show that this is in trace class. You can compute the trace norm for this guy. And you can explicitly show that it goes to 0.
So you suppose typically fk to decrease exponentially or something like this?
Sorry, that.
So here the fk go to 0 at which speed, exponentially or?
No, they could go like 1 over k is enough. You just need C1 or something. In fact, actually, the only thing you want is that this is finite. Okay, so this needs to be finite, and this is multiplying the Fourier coefficients with k. So this is, but only square root k actually. So it's basically a half derivative. So what you want is that this function has a half subleft norm that is finite. Okay, so then it all makes sense. Okay, so that's and actually under that condition you can also show that this converges in trace norm. So actually, so you don't need very much. So you don't need exponential decay, although in our case it will be exponential decay, but you don't need that. And you will never use this in the proof either. And the proof doesn't get easier either if you're showing somehow. You get everything immediately. Okay. Yeah, so is it clear? And just already a little reminder, I mean, we see that we have this f plus and f minus. This reminds us a little bit of the, we know factorization. Right? And actually, I will give now just an operated theoretical proof, but there's a second proof using Schur measures where actually you actually recognize this as the correlation kernel, like a point process. So that's the second proof, but I don't want to. There is a relation already there. Okay, so that's the second proof. How do we do the first proof? Let's continue on this. So,
excuse me, just as a stupid question, is it a how to say h or plus I?
No, here, this is uppercase, both. It's h times h.
Okay.
So it's a qn times h times an h times a qn.
Okay. Thank you.
Okay, so we're gonna prove this. Okay, and I'm gonna prove that theorem, so I can erase this. Okay, so to prove this, I have to prepare some things, and I will start with my favorite math formula of all time. So I will call so then I should not call a proposition, but let's call it the theorem because it's a beautiful theorem. It's the Helton how Pinker's determinant formula. And this is really a beautiful identity. It says if I have two operators, A, B, this is very general. So let's say that we're working on some Hilbert space, and these are bounded operators on a Hilbert space. Okay, so this H here is a complex Hilbert space. Bounded operators are a complex Hilbert space, and bounded, but nothing more than that. So not compact or anything. But let's assume that the commutator of A and B is trace class. Okay, now I didn't really know if I spoke about trace class operators. Those of you that know it, fine. If you don't know it, just say finite rank. Okay, that's, finite rank is enough. just think that this is just basically this is a matrix. Okay, but so it's just find blank. If you really want the definition, like find out, it's trace class operator is an operator for which the singular values are summable. So if you define the eigenvalues of the adjoint, this matrix times is adjoint, and then you take the square root, and if that's summable, then it's trace class, and then the frontal determinant makes sense. So just to make sure that the determinant makes sense. So then we have the following identity. The determinant of e to the minus a times e to the minus b times e to the a plus b. This is the determinant. This is e to the half times the trace of the commutator of a and b. So this is, I love this form. So let us absorb this formula a little bit, because every time you use it, if you see this for the first time, you think this is nonsense. Because the determinant of the product of operators, it should be the product of the determinants. The determinant of the exponential should be just the e to the trace of a, right? If I take the determinant of a should be a to the trace, the product of the eigenvalues. The eigenvalues are e to the eigenvalues of a, and then just take the product, which is just e to the sum of the eigenvalues, right? So if I do that, I get the trace of a minus the trace of a minus the trace of b, trace of a plus b. Well, then everything cancels. This should be 1. So, and that matches also because we know that the trace of a and b, well, the trace of ab is the trace of ba. You probably have taught that in linear algebra. So yes. So am I writing nonsense here? No, I'm not writing nonsense. Why? Because these are operators. And for operators, you cannot, the determinant, I claim that this is true if this operator is trace class. If this operator is nice, then it's true. But in general, it's not true. I mean, the determinant you can think of as the product of the eigenvalues, but the product of eigenvalues for operators might be divergent. So it doesn't. So I cannot take the determinant. And this is also true, right? I cannot. This is not defined. I cannot take the trace of these operators. I'm taking basically infinity, and I'm saying it's equal to infinity. But I can say infinity minus infinity, and that can be whatever it is, right? If you so this is you cannot use this identity. However, if you know that the commutator of the two is nice, then it's correct. I love this formula. I love this formula because the first time you think about it, this is complete nonsense. And that's my first reason I like it. The second, the proof is rather elegant. And the second reason is that this is behind a lot of beautiful. This is the reason why. So if you know already about Gaussian fields appearing in random matrix theory or in random tilings, this identity is what is behind it. It's really, in the end, it boils down to that. So it's a beautiful identity, and the proof is actually, okay, so I was thinking of giving a proof of this identity, but it's, there's a proof in the notes, and maybe I will not do it. I will just say a little bit how it works, because it connects to something very beautiful. Okay, so the proof, so let me just say the proof. Let's come, you can form this determinant. I put a t in front of it. Yes, I put a t in front of it, and then you are going to compute the log derivative. So you are going to look at the d dt squared of the log of ft, and you show this is the commutator of AB in the trace. Okay, and the proof in the notes. Okay, it's a tedious computation, or not tedious actually. It's a nice computation, but since I'm already a little low on time, I will not do that. Okay, and why do we get a trace? Well, we start with a determinant. You take the log of the determinant, log of the determinant is the trace of the log, as long as things are well defined. Then you take a derivative, and then you take a derivative, and then okay, you see what terms come in, and then you just show that it's this. Okay, it's not a trivial computation at all, because in the end you will use that the trace is cyclic, but you can only use it when the matrices are, when one of the matrices is trace class. So it's a subtle computation. Okay, so this is a subtle computation. So I'm going to give another proof, which is a bit of a hand-waving proof. But those of you that know something about Lie algebras will like this very much. So this is called the Baker-Campbell-Hausdorff formula. Baker-Campbell-Hausdorff tells you, for example, if you have an e to the x and you multiply it with e to the I, and let's say that these are matrices or whatever you want, then this is e to the x plus y, but it's not quite that. It's going to be, well, it depends a little bit what you want. It's going to be something. You can write this as a product of maybe a commutator of x and y. And you can take another product here with, so actually I should write this differently. This is the e to the x plus y, is e to the x times e to the y, and then we have some formula with nested commutators. Okay? And okay, now I don't take this too serious, okay? And because there are some factors here and I don't know them by hand, but there is a nice way of writing, just for general, there's a formula which is, actually this is called the Zassenhaus formula. And it follows from Baker-Campbell-Hausdorff formulas, is that if you take the sum of an exponential of a sum, then it's the product of the exponential, but you have to make up with commutators.
It keeps going, right?
And it keeps going, and it keeps going, and it keeps going. So that's why since it's going, that's why my proof is not rigorous. Okay. Right? So if I bring these two on the other side, right, I get e to the minus y times e to the minus x, I get a product of all these exponentials. And it keeps on going and keeps on going. You get nested commutators and commutators and commutators. But now, if I take the determinant of this guy, that's the determinant of the product. And now I can take the determinant of the product because each of these, this is trace class. So then I get the determinant is the determinant of the individual terms. Because everything is trace class, I can take the product of the determinants. And the determinant now is e to the trace of this, which is the first term here. And here I can actually use the cyclicity of the trace because this is trace class. And trace of AB equals the trace of BA if A or B is trace class. So these nested commutators, they don't contribute. They all give trace 0, because then you can use the term. But here you cannot. Here it might be something. So it really connects to Baker-Campbell-Hausdorff, actually, and Zassenhaus formula. It's a beautiful formula. So if you like this kind of theory, that this is what is behind. It's really nice. But I mean, there's a proof in the notes that doesn't use this because you have an infinite product and you have to justify things. But I think this is the way to remember it. And then a proof is a careful estimate of what I did.
So does this theorem in particular say that the determinant of the left-hand side is well defined?
Yeah, it also says that, yes. Because, exactly, because what you need to do is you need to show that this is 1 plus a trace class operator. And what you do is that you actually, this here has an expansion in terms of commutators. Yes. So it also shows exactly that. I mean, good remark. I should have put it as a theorem. The theorem of the determinant is well defined. Even though the determinant of the exponentials is not well defined, the product of the exponentials. Okay, very nice. So there is a corollary to this statement, and that's the way how we're going to use it. If I take the determinant of e to the minus a times e to the minus b times e to the a times e to the b. This is e to the trace of a and b. Okay, so you drop a half, and then it's the product of those. This is okay. This is actually just a corollary of this one, because you know, if I can insert here an e to the a plus b and an e to the minus a plus b, and then I have a product of two terms, which gives me both the same exponential, and then this half just get doubled. That's a nice little trick. And this is actually the more classical one. Actually, this is the more general one, but the other one is the more classical one. So let me show that this is really, that we're not doing nonsense here. Let me really show that this is, is really nice. So let's compute now the determinant of e to the minus t of f. T of f plus e to the t of f minus. Yes? Sorry, plus e to the t of f plus e to the t of f minus. Yes, I will compute this one. Okay? So now we're just taking, for our a and b, I'm going to take Duits matrices. Is it clear what I wrote? It's a Duits, and f here again is f plus f minus as before. I claim that, you know, here it gives a very nice answer. Because remember, for Duits matrix, we had this following rule. If I take a product of two symbols, I get the product of the Duits matrices, but I also get this. And okay, so if I take now the commutator of t of f plus to t of f minus, what is it? Well, it's the t of f plus times the t of f minus minus the t of f minus times the t of f plus, right? And t of f plus, okay, but then I can, this is just, okay, so this is just the same as minus of the h of f plus times the h of f minus. And then I also get the t of f plus. But here I can actually just think, okay, that's just it, this is it. Right? So if I apply this theorem, what I will get is e to the half, and you can just check it. You have to check, you have to now take a and b to be tf plus and minus tf minus, right? If you just take it, what you get is the trace of h of f plus times the h of f minus twiddle. Right? We have a twiddle.
What is there a half?
Sorry?
What is there a half?
There is no half. And this is a Hankel matrix, right? It's a product of two Hankel matrices. It's a little exercise to the rear. This is e to the sum over k is 1 to infinity to k times f times f minus k. Just compute it, okay? And that's the term that we saw in the strong-Sabin theorem. It's very beautiful. So you see already that for Duits matrices, it's okay, right? So the point is that our operators, Duits operators, they're bounded operators, and they are really not compact, right? I mean, they have really full rank. I mean, these are definitely not compact, right? But these Hankel matrices, the values decay, so they're much nicer operators. So they are typically are compact and actually even trace class or even finite rank somehow. So you can, the Duits matrix can have full rank, but the Hankel matrix can be a finite rank. And the commutator of the Duits matrix is okay, that's a product of Hankel's, okay, so that's nice. So this theorem applies perfectly. Of course, when F is, when the Fourier coefficients don't die enough, this fails. And this is an interesting case. This is called Fischer-Humphrey asymptotics. This is related to Fischer-Humphrey asymptotics, which is an whole topic on its own. So that's very nice. Okay, so now let me get to the proof of the Boving-Kunkov identity. And there is only one more, no, sorry. There is one more theorem, little lemma that I need. And I don't know if this is known to you, but if you have a matrix A, right? So let's say that we have a matrix A, and here we have an AI, and here we have the AI complement. So we take sort of like we cut it into two pieces. Yeah. Like you have this is sort of a minor. So if you take a submatrix with the indices I, and then you have a submatrix with the right like this. And there's a statement that says that the determinant of AI equals the determinant of A times the determinant of A inverse I complement. Am I doing this right? Yes. Right. So this is, I mean, this is just linear algebra. This is just a Kramer's rule. Actually, I don't know which Kramer it is. Is it, no, I don't think it's the French one, right? No, that's with a K, is it, right? So maybe it's the Dutch one, I don't know. Kramer's rule, that's for computing the inverse, but this is not for subs, for principal minors. If you compute the principal minor of one submatrix, right? Then I can just go to the complementary minor for the inverse at the cost of computing the determinant of the whole matrix. That's a standard trick. Again, you know, I told you this course is full of tricks from linear algebra. This is one of them. The way you proved it, the sure complement formula with the table solution. There is a proof in the notes. Okay, very good. So now I have everything ready for proving the Boving identity. And it starts with a bunch of observations, okay? So I start with e to the f, okay? This is e to the f. This is where I started with, right? So there's a bunch of claims, right? So first of all, I write this as f minus times e to the f plus, and then I can say this is t of e to the f plus times t to the e to the f minus. Okay? There is no Hankel part because the right part has only negative Fourier coefficients. There's only positive Fourier coefficients, so if I take, right, so this one here is only negative Fourier coefficients, so the Hankel matrix for this guy is 0. Yes. Okay? This is an obvious thing. So this is the first claim. That's one. Second, note that this is actually so these are upper triangular. This guy here is upper triangular, and this is lower triangular. I claim that I can write this also as e to the t of f minus times e to the t of f plus. Is that clear? So the thing is, if you write this as an exponential, you get products of t of. Basically, what I'm saying is that t of f minus times t of f minus is just t of f minus squared, right? Because the Hankel parts disappear. And I can take higher powers and higher powers, basically I claim that the t of f minus to the k is just nothing else than t of f minus to the k. Yes. Because the hyper parts always disappear. So I can sort of, in general it's not true, right? T of e to the a, e to the f is not e to the tf, but if it's triangular, then it's true. Very nice. Yes, that's okay? That's the first trick. Now it comes a beautiful trick, another trick. If I take the Pn of e to the t of f plus times the Pn, and I take the minus of this, and I take the determinant of this, this will be e to the minus n times f naught. This is not very difficult. Why not? Because I just told you that if this is a triangular matrix, right? So e to the is also a triangular matrix. So we just take the product of the entries on the diagonal, and the entries on the diagonal are just the zero Fourier coefficients of f. I included it in plus. So that's this. I can also do this with minus. And then maybe you just get 1, because with the minus sign, I didn't include the 0 here, right? So I take the f plus, it's including 0, and this is without 0. Yes? Okay, but then 4, that e to the minus n times f of naught times the determinant of Tn of e to the f. If I just use these formulas, I can write this as the determinant of Pn of e to the t of f plus with a minus Pn times t of e to the t of f minus times e to the t of f plus times Pn times e to the minus t of f minus Pn. Yes, because this is a determinant. I can actually first write this as the product of the 3 determinants. And then I just write that the product of determinants is the determinants of the product. Right? So we have this term, I just put it there. Then we have this term, so then we have this term, but I write it like that. So this is this term, and then we have this term. Yes? I just put the product of the 3 terms. And now comes the crucial step. Yeah, okay, maybe I'll wait until I go into it. Now is a crucial step. This is a lower triangular matrix. This is a lower triangular matrix. Right? This guy. I'm cutting the nth. I'm cutting at the nth columns, and I only take a look at this part. And this I throw away. Yes? I'm also cutting only the first n columns. But wait, since it's lower triangular, these were already cut. Right? If I take the first n columns, then I already threw also so the first n rows, and actually, these columns are all trivial, so actually I can remove this Pn for free. By this triangle. So this is the determinant of the Pn of e to the t of f plus times e to the t of f minus times e to the t of f plus times e to the t of f minus to the minus here. I hope I did it right. Yes. Times the Pn. Yes? Okay, very good. But now I'm done. Why am I done? Because I can just use the Jacobi identity, this is just the determinant of the e to the minus t of f plus times e to the t of f plus f minus times e to the t of f minus times e to the minus t of f plus times the determinant of the inverse of this guy and the complementary, right? The complementary part. This is where the Qn come in. This is the complementary part. So this is going to be the determinant now of the inverse. So it's basically Qn. So it's like, I put the Qn here of e to the t of f minus times e to the t of f plus with a minus e to the t of the f minus with a minus times e to the t of the f plus Qn. Because, you know, if I invert this product of exponentials, I just invert each exponential and reverse the order. So this guy becomes the inverse of that. This minus becomes a plus. This plus becomes a minus. This minus plus becomes a minus. This minus becomes a plus.
And about, did you reorder them by somehow?
So did I screw up this guy?
This, I think the second and the third term are the other way around, or no?
You're right. Yes. Yes? So Jacobi identities, right? So this is Jacobi. So now I can just use my formula that I like so much, because this determinant of the product of the operators was just e to the sum of k times f minus k. And what is this? Well, let's see a little bit. It's Qn, but I can. Oh wait, I can actually bring the t in front, and right? I mean, does everybody see that this is e to the f minus f plus? These two guys, because I can. These are triangular, so I can bring the t in front.
Same trick as before.
And the same trick as before. You put the t in front. And then you use the fact that if you have this, okay, they're the product of two Duits matrices, but now they are the right triangular form, so I can just multiply the symbols. And here I get e to the minus f minus plus f plus. Okay, that's very nice. So let's do it one more time. We have a product of Duits matrices. That's the product of the Duits matrices. That's the Duits matrix of the product, but maybe we have to take the Hanko part in account. We didn't have to do it here, but now we have to. And you see that this is the inverse of that, right? Because the f minus comes with a minus, and here it comes with a plus, comes here with a plus. This is just the identity minus h of e to the f minus f plus times h of e to the minus f minus tilde plus f plus tilde Qn. And that's what I promised you. It's beautiful. So yes, so that's, is that clear? Yeah. Okay, so that's the proof basically. It's a very useful identity to have. And we might see it coming back in the next lectures too. It's really it's a very beautiful thing. Okay, so now let me get back to the to applying this theorem to compute. Actually, we don't really need this theorem, but we just need the strong single limit theorem actually to compute the partition function. But I might say a few words. more. So now there's a theorem. Let's take the Aztec Diamond. Size n. With bias parameter A. Okay, so we have this again, right? So basically the probability of a given tiling is proportional to A to the number of vertical dominoes. Yes. So let's give the weight of a tiling. Let's let it be like this. Let's give the weight of a tiling to be like this. And I claim then the sum over all tilings will be 1 plus a squared plus n times n minus 1 over 2. So the number of possible tilings of the hexagon is 2 to the n over n minus 1 over 2, right? Because if the weight here is an a is 1, and I take the total weighted sum, I just get the total number of tiles, and it's 2 to the n times n minus 1 over 2.
The tilings
Of the Aztec Diamond of size n.
you will have hexagon.
Oh, of hexagon. Of the Aztec. And the proof is now when we have the strong-stick limit theorem. Actually, it's rather easy, but there is this annoying twist. There's an annoying twist that we have to strange domain. So there is a dilemma. Take the symbol a of z is 1 plus az to the n times 1 minus a over z to the minus n. Take this symbol. Then for any n bigger than capital N, we have the determinant of Tn of A equals Zn times Zn minus 1.
And Cn is this partition function.
And Zn is the partition function. Yeah. So this is Zn. And the proof of this lemma is as I said before. You just take this, you take this larger domain. You just see that your partition function just factorizes because no tile can overlap regions. So these are basically 3 independent regions. So the total weighted sum is just the product of the total weighted sums of the 3 individual ones. The corridor has weight 1, is trivial, so we don't forget about that. And then we just have 2 Aztec diamonds, one of size n and one of size n minus 1. And then you say, okay, but this was the same as the second pass. There was this LGV theorem, and the LGV theorem told me that this is the determinant of all the paths going from left to right, and that's the Tn of A. And because these are the transition matrices to go from one step to the other. Yes?
So does it give a way of sampling random tiling of size n, starting from a random tiling of size n minus 1? Let's say I want to do simulation.
Yes, that's not really what I'm doing. So that's another way of doing the partition function. That's not what I'm doing here.
Mm-hmm.
I will do this in the next lecture.
Okay.
So that's an easier way actually to prove it. But I want to show off some strong single limit theorem. That's actually an easier way. And this way that I do here also applies to other types of models. As long as you have as long as you write non-intersecting paths, you can always find, and because for in general non-intersecting paths, the partition function of the non-intersecting path ensemble is a Duits determinant. And so the strong single limit theorem tells you what is the limit. And this helps for all n bigger than n, so I can also take the limit from n going to infinity. And now I just apply strong single limit theorem. Okay? You have to compute the strong single limit theorem, but we already have the Wiener-Hopf factorization, so we know we write this as an exponential form. It's the log of 1 plus az, and then 1 minus the log of 1 minus az. You just plug it into the formula, and this gives you 1 plus a squared to the n squared. Okay, but that doesn't give you Zn, because it gives you Zn times Zn minus 1. But okay, if you have Zn times Zn minus 1, so the next steps to the proof of this theorem just says that Zn is Zn times Zn minus 1 over Zn minus 1 to Zn minus 2 times Zn minus 2 times Zn minus 3 over Zn minus 3 to Zn minus 4. And so on. You write a telescoping, product until you hit 1 or 0, and then you know that okay, you compute it for the size 2. For the size 1 I can compute. There are 2 possibilities, right? So, and for size 2 I can also compute it. There are 8 possibilities. It's not so difficult to just do it by hand, and this will tell you that that you get this formula. It's just you just plug in this formula, so you get basically 1 plus a times n squared over 1 plus a, there's a square, times n minus 1 squared times and so on and so on and so on and so on, right? And you see what happens in this sum. This is what will roll out. Okay, that's the computation. I don't want to do it. Yes, okay, so now I have 10 more minutes to do some symmetric function theory. So
More than 10 minutes, right? It's quarter to 1, right?
is it again quarter to 1?
Yeah.
Yes.
It's quarter to 1. I constantly make that mistake. Okay, great. So then I actually have some more time. Okay, that's great. Why do I constantly make that mistake? Yeah, last time also I was. Sorry about that. I think the first 2 times it wasn't a quarter past, so it's stuck on my hand. Okay, very good. Okay, so okay, great. So then I actually have some more time to speak. Okay, so that's so it's clear now why this is true, right? So how to prove it? Okay, so this is clear. Okay, very good. So I guess it's also clear that you can do this more generally, right? So we will actually do this a little bit more generally now. So I still have time to talk about this, so that's great. So I'm going to go to the next topic. Okay, so any questions about this? Because then no? We will do this again, and I will. So maybe let me, before I start that, to motivate it, there is a very beautiful story about the Boolean group of identity. It's called the Boolean group of identity, right? Because it was found by Boolean group. And it was found in, Duits determinants and the strong single limit theorem goes back already like 100 years or something. So Duits is like trying to find these kind of theorems, the weak single limit theorem and strong. This is really a long history, and people like Sego have worked a lot on it. Harold Wither have made major contributions. He really made very nice contributions to this theory. Lots of people looked at it, Baser, Britcher, like lots of people. And then at some point at a conference, I believe it was in '99 or somewhere, like early 2000s, it was Percy Date who asked the question. So in a conference he was working on some Duits determinants, and he actually mentioned that somehow it should be possible not to just derive the strong single limit theorem, but there should be some determinant of this operator. There should be a correction term, something of this type. There should be some kind of fractal determinant identity. I don't really know how he came to that conjecture, but he said, like, I feel something like this should be, we should find an expression for that. And, in the audience were Borodin and Kunkov, and they sort of immediately realized how to do this. They said, yes, of course, this is trivial. And you can write an identity like that. And really, so the people, Turkish people were in the room, really, can you do this? Yes. And they basically wrote a very short paper, very short proof, very highly cited. It's very highly cited, and it came as a complete surprise to the people working in Turkish theory, who got very frustrated and annoyed that they came up with a proof immediately. And so in the half year afterwards, at least 4 or 5 different proofs, or 4 or 5 papers appeared with each 2, 3 different proofs of this identity, to make, using operator approaches to make sure that you don't have to use the approach of Borodin and Kunkov. So they were completely surprised that they missed this.
This is cheating a lot, no? If you know the answer, it's much easier to find the proof.
Yes, exactly, yes. But you know, that's why they came up with so many. So, right. Exactly. So this was this was interesting. And then it turned out that after a year later or something, Geronimo and Case, who were working on scattering, inverse scattering theory, they said, wait, why is everybody making such a fuss of this identity? Because I believe we have this identity somewhere in paper. And already in the 70s, it was written in a form that it's not so easy to recognize, but yes, they actually have this in paper. So nowadays we call it the Borodin and Kunkov identity, but it should be called the Borodin and Kunkov Geronimo Case identity. But what I want to present to you today, maybe in 5 minutes, is like how they came with this, with a very simple proof. Why for them it was completely simple from symmetric function theory. Okay. I mean, I will cheat a little bit. It's not that it's trivial at all, because you have to go through some machinery of symmetric function theory, but they were exactly working on that, and for them it was sort of an obvious thing. Okay, and one of the important points is that we will see is that this operator, I'll identify this extra term as a gap probability for the determinantal point process. Okay? And that's basically their observation. So they constructed a determinantal point process, which we basically already have seen, but I will say it in a few different words. And then there was another identity they used for that process called Kessel's identity, which gives basically the full answer. Okay? So for them it came out very, very natural from the theory of symmetric function theory. Okay? And I just want to be very quick today now, so I will just indicate a little bit how they were thinking and how it's going to be used, because it's a very beautiful proof as well. So this will be a very, very much of a crash course in symmetric function theory, and probably you're very unfortunate that I'm the one doing that, because I know very little about this. I've seen lots of things, but I've never really worked on the combinatorial details. So I'll give you just a very quick course. Okay. So what we'll start with is with the space of symmetric polynomials in n variables. There is a way of making this into infinite variables, and that's, for example, one part that I don't want to talk about. Okay, so I'll just do this in n variables. Okay, so I'll write Ln. Sort of this is the ring of polynomials. And so these are variables, these are just some abstract variables, commutative abstract variables, x1 to xn, and we just take polynomials in them over the complex numbers. And it has to be symmetric. So if I take a polynomial and I permute any of the variables, it gives the same answer. It has to be symmetric. Okay, so let me give you some examples. Okay, this is a huge space, of course. So let me give you some examples. One example is kx1 to kx capital N. This is the sum of 1 less than I1, less of equal, very important, write equal in your notes. AK, right? So here it's k is less than n of x I1 to x ik. I just take products of different x's, but they actually don't have to be different. So I could also take powers, right? So, but if I write it in the sum, it will automatically be symmetric. Okay, and these are called the complete symmetric. These are the complete symmetric. Polynomials. And then you also have the elementary symmetric polynomials. These are a k of x1 to xn, and these are exactly the same sum, but now I have strictly different. It's not the same, so there's no equality. So these are really different variables. So you don't have any product of powers. Okay. Yes. Very good. So these functions, there's a way of organizing them. I can write, if I write h x of z, this is the sum over k and 0 times hk of x. I'll write just x, but I mean the tuple of z to the k. And then I write this part, and then it's a little exercise to the reader that this is actually nothing else than the product of j is 1 to capital N of 1 over 1 minus xj to the z. Okay, and then the same thing for the complete symmetric functions. This is 1 plus xj times z times the product. Okay, this is just some little claim. You can just my handwriting gets worse. Okay, so this is basically just the so note they are sort of related because the hx of z times this is 1. Okay, this is 1. Okay, and these are some nice functions because if you look at the space of, if you just look at the complete symmetric functions, they generate a whole algebra. You can write any symmetric polynomial as a polynomial in these variables, hk, and the same for ek. Okay, so they really build your entire space. There is another polynomial that we like, and that's the Chaire polynomial. Okay, and the Chaire polynomials, they are defined, they are indexed in a little weird way. They are indexed by partitions. Okay, so I have a lambda, which is just these are integers and they are ordered. Okay. Yes. Actually, we could have. Sorry, I should have. I want arbitrary sign. Sorry, I just want to have arbitrary. Yes. Okay, and these are all integers. So this is these are all integers. So these are all ordinal. Okay, with including 0. And well, a long story short, so I'll make a little shortcut. Then I can define now the. So there is a much longer story in the notes, but because of time, I'll just cut right to the core. You can define the Schur polynomial as lambda of x. This is what? This is the determinant of what? Of these complete geometric functions, the complete symmetric functions, lambda I minus I plus j x1 to the x capital N, divided by the determinant of x I to the n minus j, and I and j run from 1 to n, and this also I and j run from 1 to n. So this is the Schur polynomial. So actually this is not really how you usually define this Schur polynomial. You define it in a different way, and then there is called the Jacobi-Trudi identity, which says that this identity is true. Okay, so just in the notes you will find a different definition, and this is a theorem, but that's the theorem that is important to us. Now we erase the Kolokov identity. So there's a lot of identities that you can prove for these functions, and there's a whole business around this. Let me maybe mention 2 identities. Okay, so I want to. The first is the Cauchy identity, and it says the following: if I take S lambda of x times S lambda of y, so I have now, S lambda has variables x1 to capital Xn, so x capital N, and y is the same. It's y1 to yn, right? So we have variables x1 to xn, but also y1 to yn. So this is a product of 2 symmetric polynomials, but they're only symmetric in the x's, symmetric in the y's, and you cannot change x or y, of course, right? So right? This here, you can show if you sum over all possible partitions, this is equal to 1 over the product of 1 minus xi times yj. And I and j run from 1 to capital N. This is the Cauchy identity. Okay, and then there is another identity that's called Gessel's identity. And it says that the determinant of t and phi, the Duits determinant, this is the psi, this is the sum over L, where the lambda n, right, this is an ordered tuple, but the first one is less or equal than n. This is S L of x times s L of y, and s of y, and psi here is e to the x of, so psi of z, the symbol, is e of x z times e of y z inverse. Yes.
What is the little indexing?
Sorry?
Yes, in this term, what is lambda 1?
So lambda is a partition, right? So for example, partitions are like 3, 2, and so on, 0 and so on, 5, 0, and so on. This is a partition of 5. So it's just a sequence, like a decreasing sequence of integers that the total sum is finite. And if I sum over this SL of x and SL of y, where I want this first integer to be less or equal than n, then it's given by Toepkins determinant. So these are two identities, and you prove these identities really using just some clever tricks. Okay? Okay? So now I claim that this is basically the Cauchy, this is basically the Bogdanov-Kunkov identity. Sorry, this is the Strong-Sekulin theorem, and this can be used to prove the Bogdanov-Kunkov identity. Okay? And I want to just...
The sum is the sum of all the partition of n.
So this is all partitions, all partitions.
No, the second guess of the identity.
So this is all partitions. Then I mean they could be the partitions. I mean the sum of the partition. I mean some of the numbers could be whatever they are. But lambda one.
Yeah, the first one. Okay.
The first one needs to be less than n. So yes. And you prove those really just using some this machinery that you develop here. I mean I don't have time to go through it. Right? It's actually not so difficult, and clever identities. It's just using clever identities all the time. Okay? Okay, very good. So now I want to go a little bit to now I can go introduce what is the Schur measure. Okay? So the Schur measure, so that's a measure of partitions that people have been studying, and it's just the product of a given lambda is just SL of x times SL of y divided by z. That's just the Schur measure. And x and y here are based. You can think of it in a very algebraic way. X and y are just some variables, right? And you can set them to numbers, or you can sort of equal. You can specialize into something. But you can also think of them basically as sort of an algebra, just in a algebraic way.
Is it a non-negative measure?
It's a non-negative measure.
So these polynomials are always, they only take non-negative values?
Yes, which is not so obvious to see maybe from the... Well, I mean, you need the axes to be... if the axes are positive, then yes. But actually, a lot of times in this theory, it's very algebraic, and you don't really care if things are positive or negative. But yes, I mean, if you specialize the x's and y's to which is real numbers between 0 and 1, this is positive. Actually, I will show you. I'll show you. Because did I remove the Jacobi? No, I have the Jacobi-Trulli identity, right? So okay, so these integers, these partitions, they are decreasing, right? But they could be equal. Okay. So now I can do something similar. I can do now a change coordinates. Define Pj, or let me define. I don't have any good letters, so let me call, Pj then is lambda j minus j. Okay? Since this is decreasing, but not strictly decreasing, if I subtract its index, then lambda 1 minus 1 will be strictly bigger than lambda 2 minus 2. So this actually gives me a point process, Yes? And if you see here, this is basically, yes. And I somehow don't like this one. Did I screw up, or am I now confusing myself? I want to have I'm screwing up something here, or not. Just let me double check this quickly. Yeah, I had to go through the, okay. Okay. Yes, of course, yes, it's okay. So this here, this here is now, I can see this as pi. And I can write this as minus j. That was what I was missing. Yes? Yes? So what you see here is a Toeplitz matrix. It's a determinant of a Toeplitz matrix. Right? And the H matrix, so these H, these are the symmetric polynomials, they have generating function given by this. So we actually get a Toeplitz, this is a Toeplitz matrix with this symbol. So I claim that the Schur measure can be actually viewed in a very nice way as non-intersecting paths that are like this. So you have a column like this. So let me just do this. This is the underlying graph. Now we go. Okay, a bunch of times we go up here. The first steps we go up. And then after some point here, we go, all these things go down. So these go all up, but then here they all go down. So we have these type 3 columns, these are type 3 columns, and this is type 4 columns. Right? And then we're looking at the middle line, and we're looking at the position of the paths. So I have a bunch of paths. Right, so I have a bunch of paths that go like this, and they go from 0, -1 again, 0 to -2, and so on. And here I have 2n -1, and they go down, right? And these paths, they're all non-intersecting, like this. I mean, I drew this picture in one of the earlier lectures, right? You remember this picture? Yeah? So we have paths that basically, we only have geometric up and we have geometric down. Right? Okay, very good. So, right? So I basically say that the non-intersecting path measure and the Schur measure are the same. Yes? So from the non-intersecting path picture, once I have this, I know that the partition function is the determinant of the Toeplitz matrix, which is just constructed out of this hxz times hy of z inverse. As long as n is large enough. So this h, right? So this h here was, so again, h of xz is the product of 1 over 1 minus xj and z. J is 1 to capital N. Because they generate my symmetric functions, and it's exactly those that you get here. These are the Fourier coefficients of this matrix, of this symbol. Wait, but then I also can take the limit n to infinity of this determinant, and what I get is this value. So this should match with the strong single limit theorem, and it does. Do the computation, the strong single limit theorem gives you the Cauchy identity. So that's a very nice way. So if you come from symmetric function theory, that's the way you prove the strong single limit theorem. You prove the Cauchy identity, and then you show that the Schur measure, actually the partition function of the Schur measure, is also a Toeplitz determinant. And you can set n to infinity, and this is what rolls out. Okay? Right? So now to complete the story, now you can also look at, for this point process, what is the probability that the first L1 is less than 1. So that means that the top path here, that's the P1, is below a certain value. Well, we know that this is just the determinant of 1 minus, because this is the probability of no Lj is bigger, right? So this Pj then here is going to be what? Right, so that the P1, so that there are no P's in Pj's in what? In n minus 1 to infinity, in n, no Pj is bigger than n. Yes? Because if L1 is less than n, then the P1, the top path, is less or equal than n minus 1, so there are no paths above n, and this is just the determinant of 1 minus the kernel restricted to n to infinity, so this is the Qn of the kernel. Yes? Qn times the kernel. For this point process that we have computed. On the other hand, I know by Gessel's identity, it's a Toeplitz determinant. I also know that this is a Toeplitz determinant, the Tn of psi divided by z. Right? Because that's also just the sum over this guy here. So the moment you have your kernel, you basically get the identity that the determinant of Tn psi equals Zn here times this determinant. And we know that this is the strong single limit theorem by the Cauchy identity. So we have the relationship that the determinant of Tn psi here. So this determinant is also Zn times the determinant of identity minus Qn times the kernel Qn. Now you have to understand that this kernel can be written in terms of this product of these Hankel operators that I wrote. That's the remaining step of the proof. But remember that when we computed this kernel, we were inverting the ground matrix. We actually got the product of those matrices, and if you rewrite out the details, you get exactly the product of Hankel matrices back. So since these identities were known to the symmetric function people, they came up immediately with this statement. For them it was a triviality. Of course, this is just, you write it like that. Okay, so I did push this down your throat, and even I still have 10 minutes, 10 minutes left. So I could have, but I hope it's sort of clear. I mean, there's a whole theory for the symmetric part. I don't want to go into that. It's very nice, actually. It's just sort of an alternative way of thinking. If you prefer that. I mean, you can either prove Gessel's identity and Cauchy identity by Toeplitz determinants, what I did basically, or you go the other way around. Good. Okay. So that's it for today. So next week there will be no lecture. We will see again in 2 weeks, and the question is also a little bit, what will I see more, right, for the rest of the lectures? I will do something, especially since it has been now asked in 2 ways. I want to go to some topics that I think are actually quite also currently very interesting. So one thing I would like to do is to study tilings with periodic weightings. So we do this setup, but it goes in a more complicated weights on the graph, and this will lead to more interesting behavior and some new structures. And so what I want to do is maybe spend at least one lecture talking about that. It will also, along the way, I'm not sure which one I will do first, but will also lead to a description of the shuffling algorithm. So if you wonder, you see all these pictures and papers, they're beautiful pictures, and you wonder a little bit, how do you generate those pictures? It turns out that there is a very nice way of generating, sampling these pictures exactly by building an Aztec Diamond iteratively. You first build one for size 1, and then do size 2, size 3, and size 4, and so on. And it's an exact algorithm. There's actually Markov dynamics on these Aztec Diamond, and it's also very interesting from a theoretical point of view. So I also want to spend some time on discussing that. So these 2 topics are definitely related. And then I might either spend one lecture on Gaussian free field fluctuations, or trying to look at models for which we do not have this nice structure. For example, an hexagon where you cannot really infer to grounding traits. What can you do then? This might also depend on interest from your side. So if there is anything you would really like to see, then let me know. That might influence my decision for the last lecture. Okay, so we see each other in 2 weeks.